In lesson 111, you'll discuss again the final transformation, which is dilations, and you'll again compare a rigid and non-rigid transformation. You need to know the difference between those two and identify the uh, reflections, and dilations of functions. So let's look at again our vocabulary. So again, remember, transformation is just simply the change in position, size, or shape of a parent function. And there's two types. The first examples that we talked about in lessons 1.9 and 1.10 is rigid transformations, where we do not change the size or the shape of the image, and all we do is simply translate it, which is sliding it or reflecting it. Today, we're going to discuss again non-rigid transformation, which actually do change the size of the image, not necessarily the shape. Obviously, we're still going to have the same shape, but it's going to change the size of the parent function. And the only non-rigid transformation that exists is a dilation, where we can enlarge an object or reduce an object by a scale factor, a number that is being multiplied to that parent function. Now, of course, there's two ways of enlarging and reducing an object. We can do it vertically and, of course, horizontally. Now, with a vertical transformation, specifically vertical dilation, we have again our parent function of f of x, and to compress it vertically, which makes it look wider, this right here would be a compression. We'll call it h of x. We create this compression h by multiplying our function of f of x with a number a that's going to be less than 1. It's a positive number again, a positive number that is going to be less than 1. And that's going to compress it vertically and make the graph look wider. If I'm going to stretch a parent function vertically, it's going to make the graph look skinnier, like this blue one here, and we'll call that g of x. And the way to get the graph of g of x is that we multiply again the value, the parent function f of x, again with some value of a. But the only difference is that that value of a is going to be greater than 1. So this is pretty much straightforward. If we multiply by a number less than 1, think about what happens again and with actual values. If I have again $100 and I end up again with only a quarter of that, so if I reduce it again to a quarter of that and I only end up multiplying by 1/4, it's going to reduce again the amount of value that I have. But if I double it or triple it or multiply by a number bigger than 1, like 2, 3, 4, then that's going to again augment the amount of value that I have and give me an increased value. So multiplying by less than 1 reduces it, compresses it, and multiplying by a number greater than 1 is going to stretch it. And the function will compress or stretch vertically by the scale factor of that number that we're multiplying, by that value of a. So our scale factor is going to be that value a. So for example, we'll go back to this one in a second. So for example, here, since my dilation is 1/4 and I am multiplying by 1/4, my function now 1/4 is going to result again in a vertical dilation, and specifically a vertical compression. So vertically it's going to shrink it, it's going to compress it by the scale factor of 1/4, because that's what I'm multiplying by. I'm multiplying by 1/4, so it's going to compress it by 1/4. Now the 8 That has to do with translations, and if you recall, again, adding 8 to the entire function, not grouped with the x, that's going to result in a vertical shift. So we're going to shift 8 units up. Now let's look at a vertical stretch. A vertical stretch is going to multiply by a number greater than 1. And on this example right here, that's represented by this 5 right there. This is how we represent on the reciprocal function that we're multiplying. We look at this number up here, and that's why I want to do this example, because it's not that obvious where we're multiplying. So we look at this number here because normally it's 1, and that number is 5. So we're multiplying by 5. And since 5 is greater than 1, this is going to result in a function that is going to be vertically stretched by a factor of 5. So this 5, again, is going to be a vertical stretch by a scale factor of 5. Now the negative sign on the outside right there, that's going to be a vertical dilation, which I don't know why I'm writing that, which simply means that we're going to reflect it, we're going to flip it vertically, which is jumping over the x-axis. So we're going to flip it over the x-axis, or reflect it over the x-axis. And the plus 7, because it's to the x, that's going to be a shift, a horizontal shift, and it's going to shift it 7 units. Positive shifts it to the left in the opposite direction. So there. So multiplying by a number greater than 1 is a stretch, and multiplying by a number less than 1, a positive number less than 1, is going to be a shrink, a compression. Now, for horizontal dilations, things again are backwards. In order to compress it, so here's the original function f of x, and in order to compress it horizontally, meaning again getting this and pulling it inwards, that's going to make the graph become skinnier. So the graph will look like this. This right here is a compression. And we'll call this again h of x. And what did we call it last time? Yeah, we'll call the compression h of x. And in order to get this red graph, this h of x, what we do to our function f is that we multiply the x values, because again it's horizontal, so it affects the x coordinates, by some value we'll call b, by some scale factor b, but that value of b has to be greater than 1. So you see, it kind of works backwards, because if we think that we're multiplying by a number greater than 1, like on the last time, that it should make it again, it should stretch it out, but it does the opposite. It actually compresses it and makes it again narrower. So just like over here, in order to get a skinnier graph, we have to multiply by a number greater than 1. Just like here, in order to make it skinnier, we have to multiply by a number greater than 1. But we don't call that a stretch. We call that a horizontal compression. We call that a horizontal compression with that number in there. So in order to stretch the graph horizontally and pull these values outwards again, and pull it out and stretch it horizontally, and get this wider graph, we'll call that g of x. We get that wider graph of g of x by multiplying the x value of our parent function again with a constant, with a scale factor, but now that scale factor again is not going to be greater than 1, it's going to be less than 1. So either way, all right, either way, in order to get a wider graph, again, we multiply by a number less than 1 to get a wider graph than what we originally had. I see a wider graph to get what we originally had. And in order to get a skinnier graph, again, we multiply by a number that is greater than 1. So the same idea happens here, but it looks backwards on this one. So on the inside, it looks like we're multiplying and stretching it because we're multiplying by a number greater than 1, but it's going to compress it and make the graph skinnier. And what looks like we're multiplying by a number less than 1 and think, well, it should make it skinnier and again stretch it, it actually again, less than 1, we should compress it. It actually does the opposite and stretches it. So again, just like how we add, that makes things move to the left, and how when we subtract, that moves the graph to the right, the same thing is happening here. And because of that, the scale factor for these horizontal dilations is the reciprocal of the number that we're multiplying by. So our scale factor is going to be the reciprocal of the scale of the number that is multiplying to the x value. And using that, that's going to help us again identify whether it's going to be a horizontal compression and a horizontal stretch. So for example, on this one right here, okay, just let's focus again on the things that we know first. All right, so focusing on having the negative on the outside, well, again, from the previous lesson, we know a negative on the outside is going to result in a reflection over the x-axis. Again, outside, that's going to be a vertical reflection. So that's going to be vertical effect. Having the 4 on the outside, again, is going to affect it vertically, and it's going to shift the graph, again, 4 units up. What the 5 is going to do, since we're multiplying by 5, that is a horizontal dilation. So it's a horizontal dilation, which means that we can again stretch it or we can compress it. And an easy trick in order to remember, again, it's the opposite. So since it's going to be the opposite, that means that our scale factor is going to be flipped. So we flip this number and think about this as 1 over 5. That's going to be our scale factor. So we're really not multiplying our x's by 5. What we're really multiplying the x's is by 1 over 5. And since 1 over 5 makes things smaller, that's the hint that I use in order to know that this horizontal dilation is going to actually result in a horizontal compression. So we do again that, and we end up again identifying this as a horizontal compression. So with the horizontal dilations, flip the number, and then using that flipped number, see what happens naturally when we multiply by that value. So if I multiply anything by 1/5, notice that the number gets smaller, so it's going to be a compression. So for example, on this one right here, since the number that we're multiplying is by 2 over 7 and it's on the inside, that is going to be a horizontal dilation. Now, whether that horizontal dilation is going to be a stretch or compression, let's look at the scale factor. Since here it says that we're multiplying by 2 over 7, the scale factor is going to be the reciprocal of that, which is 7 over 2, which is in decimal format is 3.5. So if we multiply anything by 3.5, naturally that value again gets bigger. So because of that, this is going to be a stretch. And we can use that again, do this first, and then that helps us identify what type of dilation this is. What type of horizontal, specifically horizontal dilation this is going to be. And then all the other stuff again is the same. The minus sign on the inside is going to reflect the graph horizontally. And horizontally, that means that we jump over our y-axis, and the -7 on the outside is going to shift the graph 1 unit vertically, which is going to be down. So let's look at some more examples. So right here, we're not going to graph this. We're just going to identify the dilation. So here, multiplying the graph by 2, again, not grouped with the x. This is going to be a vertical. So this is a vertical dilation. And because we're multiplying by 2, it is going to be a stretch. So right here again, let's just identify the dilation. Because we're multiplying by 3, again, ignore the negative. The negative, remember, flips it. But because we're multiplying it by 3, this again is going to be a vertical dilation. Because it's not in parentheses with the x. So it's going to be a vertical dilation. And it's going to, again, be a stretch. This right here, since we're multiplying again by 1/2, and again, notice that it's not grouped inside the parentheses like the -3, this again is also going to be a vertical dilation. And because it's 1/2, this is going to be a compression. And again, as you see, this is what I want you to get clear at. Notice again that we're not grouping again. So this is a vertical dilation. And because the number that we're multiplying is 1/4, that's going to be again a compression. So the only ones again that is the opposite is going to be the horizontal one. If we had again that 1/4 grouped again with the x. So while this is a compression, if I had f of x equal to negative still, but the 1/4 in with the x to the second power plus 5, this is a horizontal dilation. And because we're multiplying by 1/4, a number less than 1, it's going to cause the opposite effect, and it's going to stretch it. So over here, our scale factor is 1/4, and over here, our scale factor is going to equal to the reciprocal of this, which is 4. So for this example, let's go back to this one right here. If f of x was equal to 1/2 inside x minus 3 again squared minus 1. So if the 1/2 again was on the inside with the x minus 3, again, the 1/2 is now a horizontal dilation. So this 1/2 is going to result in a horizontal dilation. And just like the last example, because we're multiplying by 1/2, this is going to be a stretch horizontally. And for the vertical one, the scale factor is equal to the number 1/2. But for the horizontal dilation, the scale factor is equal to the reciprocal of this. So it flips it, and our scale factor is equal to 2. So one more, okay? This one right here. With the 5 being on the outside, this is going to be a vertical dilation. where multiplying by 5 is going to stretch it, and our scale factor is equal to 5. But if it was like this, if the 5 was on the inside, again, grouped with the x and then raised to the second power, like here on the right, then this would be a horizontal dilation, and multiplying by 5 would compress it, because the scale factor is going to is the reciprocal of this. The scale factor is 1/5. So this is again the result of what is going to end up happening again with these graphs, vertically compared to horizontally, and what they look like and what the scale factors are. All right. Well, again, thank you for watching. If you do have any questions, please send me a message on Remind or through email, and I hope you have a great day.